Welcome to Orbit Observer. Settle in. Get comfortable. Pull the blanket up to wherever it feels right and let your shoulders come down away from your ears. There's nowhere you need to be for the next little while. Nothing to solve, nothing to hold, just a quiet voice and a small cold world very far away and all the time in the world to drift toward it together. So let me tell you something strange to fall asleep to. Somewhere out past the asteroid belt, circling the largest planet in our solar system, there is a moon. It is a little smaller than the moon you already know, the one that hangs outside your window at night, the pale familiar face we've all looked up at 1,000 times. Smaller than that. And yet, tucked beneath its bright frozen skin, that small moon holds more water than every ocean on Earth combined. Not a little more, not the same amount. More than twice as much. By some estimates, closer to 3 times. Let that sit for a moment, the way you'd let warm tea sit before the first sip. Every ocean on our planet. The Pacific, wide enough that you could drop every continent into it and still have room left over. The Atlantic, the Indian, the Southern, the Arctic. All the seas, all the gulfs, all the trenches, every drop of every body of salt water our world has ever held. Gather them up in your mind. And now understand that this little moon, this frozen pebble orbiting Jupiter, holds 2 to 3 times that much liquid water, hidden away where the sunlight never reaches. Its name is Europa. And here is the first gentle knot in the story, the first thing that doesn't quite make sense until you slow down and look at it closely. How? How could something so small hold so much? Our moon is bigger, and our moon is bone dry. A grey dust-covered desert with not a single puddle anywhere on it. Earth is enormous by comparison, and even Earth, the blue planet, the water world, holds less than half of what this tiny moon is carrying. It feels like a trick. It feels like the numbers must be wrong somewhere. They're not. And the answer to that little riddle is the whole reason we're here tonight. So let me walk you toward it slowly, the way you'd walk down a quiet hallway with the lights already dimmed. The trick is in where the water sits. On Earth, our oceans are, in the grand scheme of things, a thin coat of varnish. I know that sounds impossible when you're standing on a beach watching waves roll in toward a horizon that never seems to end. But think about the whole planet, the entire ball of rock spinning under your feet, thousands of miles of stone and metal all the way down to a core hotter than the surface of the sun. Against all of that, the water is barely a film. If you shrank the Earth down to the size of an apple, the oceans would be thinner than the skin of that apple. A wet sheen. A glaze, that's all our seas really are, spread out over an enormous surface. Europa does it the opposite way. Europa doesn't carry a thin sheet of water over a huge body. Europa is small, yes, but its water isn't a coat of varnish. It's a shell. A deep global shell of water and ice that wraps the entire moon from pole to pole, and that shell is roughly 100 kilometers thick. 100 kilometers of water. Everywhere. All the way around. There is no coastline on Europa. There is no dry land poking up through the sea. The whole moon is wrapped in one single unbroken layer of water, frozen hard on the outside, liquid underneath, and that layer goes down and down and down in a way no ocean here ever could. So that's the resolution to the first little puzzle, and I want you to hold on to it because it's the foundation of everything else tonight. Europa wins the contest, not because it's big, but because its water goes deep and covers everything. A small moon with a deep, global sea beats a big planet with a shallow, patchy one. It's not that Europa is a larger world hiding more. It's that Europa is a smaller world built almost entirely around its ocean. Now, before we go any further, let me make you a quiet promise about where this is heading so that some part of your mind can relax and stop wondering. Because the water is only the beginning. The water is the thing everyone already knows, the postcard, the headline. But in just the last few years, in 2023 and 2024, brand new eyes and brand new instruments turned toward Europa and found things that changed the whole conversation. One discovery made the case for life on that moon suddenly stronger in a way that genuinely surprised the scientists who found it. And in almost the same breath, another discovery made that same case for life a good deal harder. Cutting against the easy, hopeful story we'd all been telling ourselves, carbon found in 1 year, oxygen shrinking away in the next. We'll get there, slowly, gently, all in good time. And there's a spacecraft flying toward Jupiter right now, tonight, as you lie here, built to settle the whole argument. But it can't land. It isn't allowed to land, for a reason that's almost sad when you understand it. All of that is coming. For now, just the water, just how deep it really goes. Because deep is the word that matters, and I don't think our everyday sense of the word quite covers it. When we think of a deep ocean here on Earth, we think of the trenches, the darkest, most crushing places our planet has. The average depth of Earth's oceans, if you took all of them and evened them out, is only about 3.5 kilometers. That's it. 3.5 kilometers of water between the sunlit surface and the muddy floor. You could drive that distance in a few minutes on an open road. And the very deepest point anywhere on Earth, the bottom of the Mariana Trench, that legendary abyss where the pressure would crumple a submarine like a paper cup, reaches down about 11 kilometers. 11 kilometers is the deepest our whole world gets. The record. The floor of the floor. Now come back to Europa. The liquid ocean beneath that icy shell, the sloshing dark sea under the frozen crust, is thought to be somewhere between 60 and 150 kilometers deep. Sit with those numbers next to each other for a moment. Earth's average ocean depth, 3.5 kilometers. Earth's deepest single point, 11 kilometers. Europa's ocean, 60 to 150 kilometers, and not just at one special trench, not just in one rare crushing spot, but potentially like that everywhere, all across the moon, an entire world wrapped in a sea that is 10 times deeper than the deepest place our planet has ever known. If you could somehow lower the Mariana Trench into Europa's ocean, that terrifying abyss, the deepest scar on Earth's face, it would only reach a fraction of the way down before the water kept going. And going. Into a blackness beneath that has no bottom you could see or feel or reach. I find that almost unbearably peaceful to think about in the way that vast, quiet things can be. An ocean with no shore, no waves crashing on any beach, no light of any kind, no fish, at least none we know of, just a still, cold, endless, dark sea, holding twice the water of every ocean on Earth, kept from freezing solid by forces we'll talk about soon, sitting patiently out there in the dark for billions of years, waiting for anyone to notice it was even there. And here's a fair question to ask. Lying here in the dark yourself, how could anyone possibly know all this? How do we know how deep the water is, how thick the ice is, what the moon is made of, when we've never drilled into it, never touched it, never even landed on it? These are numbers about a world hundreds of millions of kilometers away, a world we've only ever seen as a small round marble drifting past a camera. Where do these figures even come from? That too has an answer, and it starts with the moon's weight. Not what it weighs on a scale, but how tightly it's packed. Scientists have a way of figuring out roughly what a distant world is made of by measuring its density, which is really just a fancy word for how much stuff is crammed into how much space. A ball of solid iron is dense, heavy for its size. A ball of loose ice is not, light and fluffy by comparison. And when you measure Europa's density, it comes out to about 3 grams for every cubic centimetre. That number is a fingerprint. It tells us Europa is mostly rock, with a core of iron down at its centre, a proper little rocky world with a metal heart, and then wrapped around all of that, a thick outer layer of water and ice. That density number is how we know the water isn't just a veneer, isn't just a thin frozen puddle on top of a dry rock. If Europa were dry rock all the way through, it would be denser, heavier for its size. If it were mostly ice, it would be far lighter. The number sits right in between, and it tells us that a genuinely huge fraction of this moon is water. Not a coating, not a garnish. A defining enormous share of the entire moon is water, and that's before we ever send a single instrument close enough to look. So the shape of Europa, as we understand it, is a little like a stone dropped into the centre of a snowball. A rocky, iron-hearted ball at the middle. Then that deep, dark, salty ocean. Then, on the very outside, a hard, bright crust of ice, frozen by the terrible cold of space, sealing the sea away beneath it like a lid on a jar. That's the world. That's Europa in one image you can carry to sleep. A rock, an ocean, and a shell of ice. And almost everything interesting about it happens at the boundaries between those 3 layers, in the places where they meet and push and grind against each other. But we're getting ahead. Slowly, there's time. Now, we have known this moon existed for a very long time. Longer than you might guess. Longer than telescopes on rooftops. Longer than photographs. Longer than electricity. To find the beginning of Europa's story, we have to go back more than 400 years, to a cold January night in the year 1610. And a man in Italy squinting through a crude little tube of glass at the sky. His name was Galileo Galilei, and the telescope he was using was almost laughably primitive by our standards, barely more powerful than a decent pair of binoculars you might buy today. But it was enough. On those winter nights, Galileo turned his little instrument toward Jupiter, the brightest wandering light in the evening sky, and he noticed something that no human being had ever recorded before. There were tiny points of light arranged in a neat line beside the planet. Little stars, he first thought. But he was a careful man, a patient man, the kind of man who looked again the next night, and the night after that. And the little stars moved. They shifted their positions from evening to evening, sliding back and forth around Jupiter, sometimes 3 of them, sometimes 4, occasionally one vanishing behind the planet, only to reappear on the other side. They weren't stars. Stars don't dance like that. What Galileo was watching on those freezing January nights in 1610 were moons. 4 of them, 4 worlds circling another planet, and just by seeing them, just by writing down where they were each night, he had quietly demolished one of the oldest ideas humans held about the heavens. The comfortable notion that everything in the sky revolved neatly around the Earth. Here were 4 somethings that plainly revolved around Jupiter instead, minding their own business, orbiting a world that was not ours. We call them the Galilean moons to this day in his honour. Io, the closest, a world of volcanoes. Ganymede, the largest moon in the entire solar system, bigger even than the planet Mercury. Callisto, the outermost of the four, scarred and ancient. And Europa, the smooth, bright one, the one hiding the ocean. Though, of course, Galileo had no idea about any ocean. To him, and to nearly everyone who came after him for the next 3.5 centuries, Europa was simply a dot, a pinprick of light beside Jupiter, a faithful little companion that appeared in the eyepiece night after night, year after year, generation after generation. Astronomers watched it, timed it, charted its orbit, and never once suspected that beneath its unremarkable glow lay more water than all the seas of home. Think about that patience, that quiet unknowing. 400 years of human beings looking directly at Europa, and not one of them, for most of that time, imagining the ocean underneath. It was a secret hiding in plain sight, out in the open, watched by everyone and understood by no one. And I want you to feel how recent our real understanding is, because it makes the whole thing more astonishing, not less. For roughly 99% of the time we've known Europa exists, we thought it was just a frozen rock. The ocean is a discovery of our own lifetimes. Some of the most important pieces of this puzzle were only fitted into place in the last few years. We are, all of us, alive at the exact moment this moon is finally revealing what it is. That dot Galileo saw is only now, in our time, becoming a world. So how did the dot become a world? How did we go from a pinprick of light to a rocky moon wrapped in the deepest ocean in the solar system? For most of that journey, the leap came from a single spacecraft, and its name, fittingly, was Galileo too. Named for the man who first saw the moon it would come to know so well. The Galileo spacecraft reached Jupiter and settled into orbit around the giant planet, and from 1995 until 2003, for 8 patient years, it looped around Jupiter and its moons. Swinging in close again and again, snapping pictures, taking measurements, drinking in data about worlds we had only ever seen from an unimaginable distance. It was the first spacecraft ever to orbit Jupiter, the first to really live among these moons rather than just fly past them and wave goodbye. And it was Galileo, the machine, that gathered the clues which turned Europa from a smooth mystery into an ocean world. But here is the part that I think is the strangest and the loveliest in this whole opening stretch of the story. The part I most want to leave you with tonight, as you drift. When we say we discovered Europa's ocean, you might picture a camera catching a glint of water, a photograph of a sea, some direct and obvious sight of waves or shoreline. That never happened. We have never seen Europa's ocean. Not once, not a single drop of it. The ice shell seals it away completely, a lid kilometers thick over the whole moon, and no camera has ever peered through to the water below. To this day, the ocean of Europa, that vast dark sea holding more water than all of Earth, has never been directly seen by human eyes or human instruments. So how do we know it's there at all? The answer is one of the most elegant tricks in all of space science, and it has to do with magnetism, so let me unpack it gently, because it's the kind of idea that's much simpler than it first sounds. You know that Jupiter is a giant, the largest planet by far, so big that all the other planets could fit inside it with room to spare. And Jupiter has a magnetic field, an invisible force wrapped around it, the same kind of force that makes a compass needle point north here on Earth. Only Jupiter's is monstrously, overwhelmingly powerful, the strongest magnetic field of any planet in the solar system. Now, Jupiter spins fast, turning all the way around in about 10 hours, and as it spins, that enormous magnetic field sweeps around with it, washing over its moons again and again, like the beam of a lighthouse turning through the dark. Here's the key piece. When a changing magnetic field passes over something that can conduct electricity, something like salty water, it stirs up faint electrical currents inside it. It's the same basic principle that runs a great deal of our world, though you never see it. And those stirred-up currents, in turn, create their own small magnetic field, a kind of echo, a response. Push a magnetic field at a salty conductive layer, and the layer pushes back with a magnetism of its own. So when the Galileo spacecraft flew close to Europa and measured the magnetism around it, it didn't just find Jupiter's field passing through. It found an echo. It found that Europa itself was generating a magnetic response, an induced field, exactly the kind you would expect if there were a large layer of salty, electrically conductive liquid buried inside the moon, reacting to Jupiter's field sweeping over it every few hours. A ball of dry rock and solid ice wouldn't do that. Solid ice doesn't conduct electricity well, and it wouldn't answer Jupiter's magnetic call the way Europa clearly did. But a global ocean of salt water would. And that is essentially the whole case. That magnetic echo, that invisible answer to an invisible question, is the strongest evidence we have that the ocean exists at all. I want you to really hold this, because it's such a quiet, human kind of discovery. We didn't find Europa's ocean by seeing it. We found it by noticing that the moon behaved as if it had one. We measured a subtle magnetic wobble, a faint response in an invisible field, and from that whisper we deduced an entire hidden sea, deeper than any on Earth, wrapped around a whole world. It's a bit like knowing there's water sloshing inside a sealed container, not by opening it, but by the way it tips and shifts in your hands. We never opened Europa. We only felt it move. And that means the ocean, this ocean we've been talking about all this time, this sea holding 2 or 3 times the water of Earth, remains something inferred rather than something touched. It is real. The evidence is genuinely strong, strong enough that essentially no one who studies these worlds seriously doubts the ocean is there. But strong evidence is not the same as a glass of the water sitting in front of you. We have deduced Europa's ocean the way a detective deduces a person was in a room from the traces they left behind, not from ever meeting them face to face. Every number I've given you tonight, the depth, the volume, the saltiness, all of it rests on clues and measurements and clever reasoning, on echoes and densities and orbits, not on any direct sight of the sea itself. We have never touched a single drop of Europa's water. In the entire history of our species, with all our telescopes and spacecraft and instruments, no human hand and no human machine has ever come into contact with even one drop of the largest ocean in our solar system. It is right there. We know almost exactly where it is. We can tell you how deep it likely runs and roughly how salty it probably is. And it remains, so far, completely beyond our reach, sealed under a shell of ice, felt only through a faint magnetic murmur picked up by a spacecraft that flew home years ago. Keep that thought nearby as you drift, because it's a thread we're going to follow all the way through this story. This whole moon is a lesson in knowing things without seeing them, in trusting careful evidence over direct sight. And in a little while we'll come to the question of what keeps all that water liquid in the first place, so far from the sun, in a cold so deep that the surface ice is harder than rock. because an ocean that far out should be frozen solid all the way down. There's no sunlight to speak of out at Jupiter, barely a candle's worth compared to what warms our own seas. By every simple expectation, Europa ought to be a solid ball of ice, through and through, a frozen marble with no liquid anywhere in it. And yet, it isn't. The ocean is liquid, dark and moving beneath the shell. Something out there is keeping it warm. Something is pouring heat into that hidden sea, enough heat to hold back the freezing cold of deep space for billions of years, and it isn't the sun. It's something stranger, something that comes from the very way Europa moves around Jupiter, from a slow gravitational squeezing that never quite lets the moon rest. That's where we'll go next. The source of the warmth. The reason the sea stays a sea. But not yet. For now, just stay here a moment longer in this first quiet image and let it settle over you like the blanket you're already under. A small bright moon, smaller than the one outside your window. A shell of ice wrapping it entirely, hard and cold and seamless. And beneath that shell, in perfect darkness, an ocean deeper than any on Earth, holding more water than every sea on our planet put together, kept secret for 400 years since a man in Italy first saw it as a dancing point of light, and known to us now only through the faintest magnetic echo, an ocean we are certain is there and have never once touched. Breathe in slowly. Breathe out slower. There's so much more to tell you, and all the time in the world to tell it. The warmth that keeps the water liquid. The ice above that refuses to sit still, cracking and sliding and swallowing itself in ways no other frozen world does. The stains on the surface that might be ordinary sea salt carried up from below. And those two discoveries, so recent, that pulled the story in two directions at once. All of it is waiting for us, out there in the dark around Jupiter, and none of it is going anywhere. For now, just rest with the ocean, the unseen, untouched, impossible ocean of a moon we've watched for 4 centuries and are only now beginning to understand. Let it carry you the way water carries anything that finally stops struggling and lets itself float. And when you're ready, softly, without hurrying, we'll turn toward the question of what keeps it all so warm. Because the strangest part isn't that the ocean is there. The strangest part is that it should be frozen, and it simply refuses to be. And the reason why has everything to do with the way this little moon is caught, held, and gently squeezed between forces far larger than itself, out there in the cold and the quiet, going around and around the giant planet, the way it has for longer than there have been eyes to watch it. But stay with me here a moment longer, before we drift toward the warmth. Stay with the size of it, because the numbers are worth holding gently in your mind, like smooth stones. Picture the water not as a lake, not as a sea the way you know a sea, but as a shell. A shell of water wrapped all the way around the moon, from pole to pole, with no shore anywhere. On Earth, the oceans are thin. They look enormous when you stand at the edge of one, but they are only a film, a glaze across the surface of a much larger rock. The average depth of all our oceans is about 3.5 kilometers. Even the deepest scar in the seafloor, the Mariana Trench, only reaches down about 11 kilometers before it hits the bottom. 11 kilometers. You could drive that in a few minutes if the road ran straight down. Now let the number change. Europa's ocean may run somewhere between 60 and 150 kilometers deep, not in one rare trench, everywhere, the whole way around. A sea that begins beneath the ice and keeps going down, and down, far past anything a diver or a submarine or a sinking anchor has ever known on our world, and it does this not in one special place, but as its ordinary, everyday self. If you dropped the Mariana Trench into Europa's ocean, it would vanish near the top like a single raindrop falling into a well whose bottom you cannot see. That is why a small moon can hold so much. The water is not spread thin across something huge, it is stacked deep across something modest. And Europa truly is modest. Its radius is only about 1,560 kilometers. Line it up beside our own moon, the pale one you can see from your window tonight, and Europa is the smaller of the two. Our moon is a little over 3,400 kilometers across. Europa is closer to 3,100. A smaller ball, hanging in the dark, carrying a deeper ocean. Let that quiet contradiction settle over you like a blanket pulled up to the chin. How do we know it isn't ice all the way down? How do we know there is rock in there at all, and not just a frozen marble of water? We know because of weight, because of how much this little world pulls compared to how large it is. Measure that, and you find that Europa is dense. Around 3 grams for every cubic centimetre, roughly 3 times the density of water itself. Ice alone could never be that heavy. So the moon cannot be a snowball, there has to be rock inside it. A rocky body, most likely with a core of iron sitting at its heart, and then, wrapped around all of that, the water. Not a thin coat of frost, not a dusting on the surface, a vast fraction of the entire moon given over to water, layered 100 kilometers thick from the top of the ice to the rocky floor far below. It's a strange thing to know so much about a place no one has ever visited, and stranger still when you remember how long we looked at it and saw nothing at all. 416 years ago, in the winter of 1610, a man in Italy turned a small handmade telescope toward Jupiter. Galileo Galilei. He was not looking for oceans, he was looking at a bright planet and the little points of light strung out beside it, and over a few nights he watched those points shift their positions, back and forth, keeping close to the planet as if tethered to it. He realized they were moons. 4 of them, circling Jupiter the way our moon circles us. Europa was one of those 4, and another astronomer, Simon Marius, noted them at nearly the same time. From that night on, Europa was no longer a random spark, it was a world with a name. And yet, for 4 centuries, it stayed a dot. A single point of light in a lens. Generation after generation of people looked up at it, and not one of them could have guessed that inside that faint speck lay more water than every ocean on their own planet combined. The ocean was there the entire time, through every war, every harvest, every quiet night any human ever spent looking at the sky. It was there, waiting, and no one could see it. So how did we finally learn its secret? Not by landing, not by drilling, not even by seeing it. We learned it by listening to a whisper in the magnetism. In the 1990s, a spacecraft named after Galileo himself arrived at Jupiter, and it stayed there, looping through the giant planet's realm from 1995 to 2003. Jupiter has a colossal magnetic field, and it is tilted, and as the planet turns, that field sweeps around and washes over its moons again and again. When a magnetic field like that passes over something that can conduct electricity, it stirs up faint electric currents inside it, and those currents create a small magnetic field of their own, a kind of magnetic echo answering back. The Galileo spacecraft felt that echo coming off of Europa. Something inside the moon was answering Jupiter's field, Something conductive, buried under the ice, wrapped all the way around the globe. And the cleanest explanation, the one that fit the whisper best, was a global ocean of salty water. Salt water conducts. Ice does not like that. So the echo pointed straight down to a hidden, worldwide sea. We did not see it. We felt it, indirectly, in the way it disturbed a magnetic field. And that is the quiet, humbling truth to carry with you as you drift. Everything we believe about that enormous ocean, we know from a wobble, a faint reply in the dark. We have never touched a single drop of it. And yet, there it is. A whole ocean, planet-sized in volume, sitting in the dark 63 kilometers beneath your feet if you were standing on the ice. You would feel nothing. You would hear nothing. The surface is quiet and pale and still in a way that makes Antarctica look busy. But underneath, something is moving. And the reason it moves, the reason it has not frozen into a dead, solid ball of ice like some forgotten marble, comes down to a relationship, a gravitational argument, really, between three moons that have been pulling on each other for billions of years. Europa does not orbit Jupiter in a perfect circle. It can't. Io is inside it, and Ganymede is outside it, and the three of them have fallen into a rhythmic lock, a pattern so precise that for every single time Ganymede goes around Jupiter once, Europa goes around exactly twice, and Io goes around exactly 4 times. 1, 2, 4, every time. Always, astronomers call this an orbital resonance, and this particular three-way version is called the Laplace resonance, named for the French mathematician Pierre-Simon Laplace, who studied it in the 18th century. The numbers 1, 2, 4 are not a coincidence, and they are not an approximation. They are a gravitational trap that the moons fell into and cannot escape. The way a marble rolled into a bowl will always end up at the bottom. What that means for Europa is this. Because its orbit cannot become a perfect circle, because Io and Ganymede keep nudging and pulling and maintaining the rhythm, Europa's distance from Jupiter is always changing slightly. Not a lot, not dramatically, but enough. And Jupiter is massive. Jupiter is more than 317 times the mass of Earth, which means its gravity is an immense, crushing, gentle hand. When Europa is slightly closer on one part of its orbit, that hand squeezes it a little harder. When Europa swings slightly farther away, the grip relaxes. And this squeezing and releasing happens on every single orbit. Every 3.5 days, approximately, Europa goes around Jupiter in about 3.55 days, and every 3.55 days, the whole moon flexes. Think of it like this. Take a piece of rubber and bend it back and forth. Fast, your hands do almost no work, but the rubber gets warm. Not because you're pumping heat into it. You're not. It gets warm because of friction inside itself, the molecular structure resisting the bending, generating heat from the inside out. Europa is not rubber, of course. It is rock and ice and iron, but the principle is the same. The flexing generates friction. The friction generates heat. Deep inside the moon, in the rock beneath the ocean, the tidal kneading produces enough thermal energy to keep that enormous global water layer from freezing. That heat is not from the sun. Europa is far too distant for sunlight to do much of anything. Out there, the sun looks like a very bright star, nothing more, and it delivers only about 1/25 the energy per square meter that it delivers at Earth. If you stood on Europa's surface and held out your hand, you would feel almost nothing from that distant point of light. The warmth that matters is coming from below, from the flexing, from the resonance lock. From Io and Ganymede, still tugging, still maintaining the rhythm, the same way they have been for billions of years. Without the Laplace resonance, there is no tidal heating. Without tidal heating, the ocean freezes. Without the ocean, the whole story changes. Everything remarkable about Europa, every puzzle and every hope, hangs on that three-way gravitational relationship. 1, 2, 4, the simplest possible numbers, and they are why something might be swimming in the dark underneath that ice. The surface itself gives you no comfort, no warmth, no promise. The equator of Europa reaches roughly -160 degrees Celsius on a warm day. The poles get down closer to -220. At those temperatures, the ice is not the soft, yielding stuff you think of when you imagine walking on a frozen lake. It is hard as granite. Geologists sometimes say Europa's surface ice is mechanically more like rock than like the ice in your freezer, and they mean it literally. You could not chip it with a pickaxe without enormous effort. It does not flow or creep the way glaciers on Earth slowly move downhill over centuries. It is rigid and cold and, on the surface, dead still. Everything interesting is happening beneath it. But here is the thing that stops you, if you sit with it long enough. If the surface is that frozen, that rigid, that old looking at a glance, how do we know anything is moving at all? The answer is that the surface is not old. Not by geological standards. Not even close. When planetary scientists want to know the age of a surface, they count craters. Comets and asteroids have been hitting the solar system for 4.5 billion years, and they hit everything they encounter. The Moon has been hit so many times that its surface is nearly saturated with craters, old ones, new ones, craters inside craters. Mars, same story. Mercury, same. The older a surface is, the more time it has had to accumulate impacts, and so the more pockmarked it looks. You can, with real precision, estimate the age of an unvisited surface just by counting how many craters you see per square kilometre and comparing that number to known impact rates. Europa has almost no craters, almost none. Its surface is startlingly, eerily smooth compared to the Moon or Mars, and the crater count, when you do it carefully, implies an average surface age of only about 40 to 90 million years. 40 to 90 million years sounds ancient to a human being, but on geological timescales, it is nothing. It is recent. The dinosaurs that walked Earth went extinct 66 million years ago. Europa's visible surface, on average, is roughly that young. Some of it might be younger still. That means the surface we see is not the original surface. It cannot be. If Europa has been orbiting Jupiter for billions of years and receiving impacts for billions of years, and yet the surface looks almost brand new, something is constantly resurfacing it. Something is erasing the old ice and replacing it with fresh ice, over and over, on a geological timescale that would look rapid in the long-run reel of solar system history. A surface younger than the last dinosaurs, and the question that should settle itself gently in your mind as you rest is a quiet one. Where did the old surface go? That question has an answer, and the answer is one of the most extraordinary things discovered about any world in the solar system in recent decades. But to understand it, you first have to see what the surface actually looks like up close. Because the smoothness is deceptive. Smooth from a distance, yes, but zoom in and the ice is anything but uniform. The most striking features are the cracks, thousands of them, crossing and recrossing the surface like veins or fault lines, or a road map drawn by someone who did not care about straight lines. Many of these cracks are not simple fractures. They are double ridges, two parallel walls of pushed-up ice with a valley between them, sometimes stretching thousands of kilometers across the moon's face. Some of them follow curving, arc-shaped paths that bend and shift direction in a pattern that turns out to be deeply meaningful. When you compare those curves to computer models of tidal stress, where the ice would crack, and in which direction, given the way Jupiter's gravity changes its pull as Europa moves around its orbit, the curves match. The cracks follow the map of forces written by the resonance. Europa's ice is showing you the record of its own tidal torment, the way a face shows the record of years and weather and expression. Every curling fracture is a scar from the flexing, a scar from the same mechanism that keeps the ocean liquid. The same force that warms the interior also tears the surface. The cracks are also coloured, reddish-brown in many places, not uniformly, but concentrated along the fractures and in certain regions, as if something has seeped up from below and been stained, which is, in fact, more or less what happened. Jupiter's radiation belts, intensely energetic particles trapped in the planet's magnetic field, constantly bombard Europa's surface. And when they hit the materials brought up through the cracks, they chemically alter them. The exact chemistry has been debated for years. But recent observations changed the picture significantly. Hubble Space Telescope data, analysed by Samantha Trumbo, Mike Brown and Kevin Hand and published in 2019, found evidence of irradiated sodium chloride in a yellowish region of Europa called Terra Regio. Sodium chloride, common table salt, the kind that sits in a shaker on a kitchen table. The implication is that Europa's ocean, or at least part of it, may contain ordinary salt water, not the magnesium sulfate Epsom salt-style brine that earlier models had assumed, an ocean that might, chemically, feel more familiar, more like the sea on Earth than like something utterly alien. The reddish-brown stains on the ice may be salt, dragged up from an ocean we have never seen, tinted by radiation. Geological fingerprints of a sea. But the stains and the cracks, as strange and beautiful as they are not the most disorienting thing the surface shows you. The most disorienting thing is what happens in the places where the ice has not just cracked, but broken, completely shattered, where the whole crust has come apart and then refrozen into something that has no good name except the one scientists gave it: chaos terrain. There are several regions on Europa where the surface looks like nothing else in the solar system. Imagine a vast plain of smooth ice, and then imagine that plain being broken into hundreds of fragments, each one anywhere from a few meters to many kilometers across, and those fragments tilting, rotating, drifting in different directions, and then being refrozen in place as the water or slush beneath them resolidified. The blocks are still there, still tilted at odd angles, still separated by the frozen matrix that locked them in when the chaos episode ended. But crucially, and this is the thing that grabbed planetary scientists, the blocks can be matched back. You can take the shapes of the blocks, the patterns on their surfaces, the edges where they broke away from their neighbours, and slide them back together like puzzle pieces. When you do that, the original intact surface reassembles. The blocks were once one continuous sheet. They drifted apart on something beneath them. And then they were frozen in place. One of the largest and most studied regions like this on Europa is called Conamara Chaos. It covers an area comparable to a mid-sized US state, and when you map it carefully, you find over 100 distinct fragments of ice, each one frozen at a slightly different angle, with the dark reddish matrix filling the gaps between them. Piece the fragments back together, and you recover something resembling the original plane. Let them go, and you have the chaotic record of a surface that once moved like pack ice, broken, drifting, rotating, before the cold reclaimed it. This is not a metaphor. The surface of Europa in the Chaos regions behaved like a frozen sea. The ice broke, the pieces floated and turned and slid, and then they froze in their new positions, preserving the record of the movement the same way a photograph preserves the record of a moment. Except this photograph is written in ice that is as hard as granite, tens of kilometers thick, and was taken tens of millions of years ago. The question, when you first encounter this, is obvious. What was under those blocks that let them move? Ice does not drift on ice. Ice as cold and rigid as Europa's surface ice would not flow or rift on its own. Something liquid, or at least soft and yielding, had to be there, briefly, in the space between the solid shell and the blocks floating on top of it. And the answer that emerged over years of studying the chaos regions pointed, again, at the ocean. Or rather, at a more complicated version of the ocean. For a long time, the dominant model went something like this. The ice shell is thick, maybe 25 kilometers or more, from surface to sea. The chaos regions form when heat from the ocean far below warms a column of ice from the underside, causing it to slowly soften and rise, like a blob in a lava lamp. The softened ice reaches the underside of the brittle outer crust, destabilizes it, and the crust breaks and floats and refreezes. Plausible, internally consistent. But it requires the heat from the ocean to travel a long way up through a lot of ice, and the timescales feel uncomfortable, and the chaos regions feel very confined and localized, not what you'd expect from a broad thermal upwelling. In 2011, a different model arrived, and it was startling. Brittany Schmidt and her colleagues published a paper in the journal Nature proposing that chaos terrain on Europa might not form above a slow thermal upwelling from the deep ocean at all. Instead, the paper proposed something more radical: liquid water lakes trapped within the ice shell itself, only a few kilometers below the surface. Not at the bottom of the ice, not the ocean far below, inside the ice, near the top. Isolated pockets of liquid water caught between layers of cold, brittle ice above and warmer ice below, held liquid by the geothermal and tidal heat moving through the shell. The mechanism they described goes roughly like this. Within the ice shell, the heat from tidal flexing is not distributed perfectly evenly. In some places, the ice is warmer. Warmer ice, under pressure, can contain pockets of slightly salty water that remain liquid even at temperatures that would freeze pure water. Think of it the way antifreeze works. Salt lowers the freezing point, so a salty solution trapped in the ice stays liquid when the surrounding ice is technically below freezing. These shallow, lens-shaped lakes within the ice could have roofs only a few kilometers thick, not 25 kilometers. 3 to 5. A roof thin enough that the overlying brittle surface is genuinely vulnerable to what is happening below. As the shallow lake's roof is heated from below, it partially melts and thins. The thinning roof becomes less able to support its own weight relative to the denser water beneath. Eventually, it fails. Collapses, the blocks of ice that were the ceiling of that shallow lake drop and float on the water surface, drifting, tilting, rotating as the shallow pool redistributes beneath them. Then the tidal heat pulse passes, or the lake drains or refreezes, and the whole chaotic flotsam freezes back into place. The chaos terrain is not the record of a catastrophic upwelling from the deep ocean. It is the record of a shallow lake collapse, just a few kilometers below your feet. The ceiling falling in and the blocks locking in their new positions as the water went solid again. This matters enormously for one particular reason. If Schmidt and her colleagues are right, then liquid water on Europa is not only present deep down in the global ocean, unreachably far beneath the ice. It is also present in the shallow part of the shell, in pockets that might be only 3 to 5 kilometers below the surface. In terms of distances, 3 to 5 kilometers is not far. The deepest oil wells humans have drilled on Earth go 6 to 12 kilometers. A sufficiently motivated and well-funded mission could, in principle, reach a shallow lake at Europa without having to drill through 25 kilometers of rock-hard ice. The shallow lake model makes Europa more accessible, and it deepens the picture of what the ice shell is. Not a simple lid, not a uniform frozen crust. A layered, thermally complex structure with liquid water at multiple depths, at the bottom where the ocean begins, and possibly near the top where the lakes form and collapse and refreeze. It also raises a strange and slightly vertiginous thought. If liquid water can exist within the ice shell, not just beneath it, and if the chaos regions are the surface record of roof collapses above shallow lakes, then material from those shallow lakes, and potentially from the deep ocean below them, which the lakes may communicate with through cracks and drainage, has been carried to the surface. The reddish matrix between the chaos blocks. The stains. Those are not just radiation-altered ice. They may contain material from the water itself, preserved in the frozen record. Chemistry from the ocean, brought up by the collapse and refreezing, lying on the surface where we can observe it from space. Which is, in a very different way, exactly what the most recent observations found. But that part of the story belongs to a later section of this night. For now, hold this image. Europa's ice is not a sealed static vault over a hidden sea. It is a dynamic shell fractured by tidal stress into thousands of kilometers of cracks, marked by the scars of places where liquid water once sat just below the surface and brought the ceiling down. The shell is actively processing material. Things are moving through it, slowly by human timescales, rapidly by geological ones. And the movement, as it turns out, is more organized than a simple series of collapses. The ice does not just break and refreeze in place. In at least some regions, the ice appears to be doing something far more structured. Something that, until Europa, was thought to be unique to one single rocky planet in the entire known solar system. But before we go there, rest in the image of Conamara for a moment longer. A field of tilted, frozen blocks, each one dark at the edges where the reddish matrix locked it in, each one preserving on its surface the scratch patterns and ridge lines of the original intact sheet it broke away from. You could stand on one of those blocks, if the radiation would let you, which it would not, but imagine, and look across the frozen chaos and see the record of a moment when the floor dropped out, when the ceiling of a shallow lake gave way, and the ice above floated free on dark water under an alien sky. And then the cold came back, slowly but completely, and locked everything exactly where it was, forever, until the next episode. A photograph in ice. A crime scene where the crime was liquid water existing somewhere it technically should not be able to, in an ice shell on a moon 63 kilometers from a buried sea, lit by a star that from this distance looks like nothing but the brightest point of light in a very cold sky. The ocean keeps its secret, deep down, sealed under all of it. The magnetic echo we detected is its voice, speaking back to Jupiter's field from its hiding place. But its handwriting is on the surface, in the cracks and the stains and the tilted blocks of Conamara Chaos. The ocean is talking to the surface. The shell is not a passive barrier. It is a conversation, ongoing, geologically slow, but continuous. And the conversation, it turns out, goes further than collapse and refreeze. The ice is not only breaking and healing in place. In at least one documented region of Europa, something is taking large sections of the surface and consuming them entirely, making them disappear. Which brings us back to the question that was left hanging a few minutes ago. The one that deserves its answer now, slowly and carefully, because the answer is one of the most unexpected findings in modern planetary science. Where did the old surface go? Planetary scientists Simon Kattenhorn and Louise Prockter spent years working on that question, mapping a particular region of Europa's surface with the careful patience of archaeologists. They were looking at the patterns of cracks and ridges, building a reconstruction of how the surface had evolved over time, the way you might reconstruct a map of a city from a series of old photographs. In 2014, they published their reconstruction in the journal Nature Geoscience, and what they found was a gap, a piece of the puzzle that was missing. They could account for nearly all the surface in the region they were studying, except for roughly 20,000 square kilometers. That area, an area about the size of New Jersey, should be there, based on the reconstruction. And it was not. It had been removed from the visible surface entirely. The most consistent explanation for where it went, and Kattenhorn and Prockter argued this carefully and explicitly, is subduction. One slab of ice slid beneath its neighbour and was pulled down into the warmer interior of the ice shell, the way one tectonic plate on Earth slides beneath another and descends into the hot mantle below. The missing ice did not evaporate. It did not float away. It was consumed, drawn downward by the denser, warmer ice below, or pushed down by the advancing edge of a neighbouring slab, or both. Recycled, returned to the interior, where it would eventually melt into the ocean, or be reprocessed by the thermal system inside the shell, and eventually come back up, renewed as fresh surface ice somewhere else. If this interpretation is correct, and it is important to say clearly that it is contested, that other researchers have proposed alternative explanations for the missing surface, and that this is active scientific debate rather than settled geology, but if it is correct, then Europa is the only world besides Earth where a form of plate tectonics has been identified. Not rock tectonics, ice tectonics. The same basic process, rigid plates forming, moving, diving under each other, being recycled, but operating in a shell of frozen water rather than a shell of silicate rock. On a moon, in ice, that would be extraordinary. The discovery of subduction on Earth in the mid-20th century was the revolution that made modern geology. It explained how mountains form, why earthquakes happen where they happen, how carbon cycles between the surface and the interior. The same process, in ice on Europa, would mean the same kind of cycling is happening there. Material from the ocean, drawn down and returned to the surface. Material from the surface, swallowed and delivered to the ocean. A shell that is not a sealed container, but a conveyor belt. This is why the answer to where did the old surface go is not just a geological detail, it is the mechanism behind everything else. The young surface, 40 to 90 million years on average, is young because the old surface is being recycled. Consumed, the chaos regions are where the ocean talks to the surface from below. The subduction zones, if Kattenhorn and Prockter are right, are where the surface returns the conversation. And both processes together are what keeps the ice so young, so fresh, so geologically alive. Europa is not a frozen relic sitting passively in space. It is a world in slow, grinding, tidal motion, its surface eating itself and renewing itself on timescales that, against the 4.5 billion year age of the solar system, look almost rapid. The ice shell, then, is not a lid, it is a living system. And the more carefully scientists have looked at it, the more layers of that system have come into focus. The shallow lakes, possibly sitting only a few kilometers below the surface in the chaos regions, connected to the deep global ocean by drainage and upwelling. The deep ocean itself, pressed between the bottom of the ice above and the rock below, kept liquid by the tidal heat that flows from the resonance-trapped moon's interior. The seafloor at the bottom of the ocean, where hot rock meets cold water, where hydrothermal chemistry operates in the dark, and the surface above, cracked by tidal stress, stained by irradiated salts drawn from below, resurfaced by collapse, and possibly by subduction. The whole moon is a system, every part connected to every other part, driven by the same gravitational engine, Io pulling, Ganymede pulling, Jupiter squeezing, and Europa flexing in response, generating the heat that keeps the whole improbable thing going. What you are looking at when you look at Europa is a world that should not have an ocean. It is too far from the sun. It is too small to have retained internal heat from formation. By the standard rules, by the rules that apply to our moon, which is also small and also far enough from the sun that its interior froze long ago, Europa should be a cold, dead, cratered ball of ice. But the rules do not apply here, because of three numbers. 1, 2, 4. Because of a gravitational accident, a resonance that the three moons fell into billions of years ago, Europa has a heat source that has nothing to do with the sun and everything to do with its neighbours. And that heat source has kept an ocean liquid for most likely billions of years, long enough for anything interesting that life requires, in terms of time, to potentially have happened. And yet, the ice keeps moving, the surface keeps renewing, the ocean keeps talking to the shell, pushing chemistry up through the cracks, collapsing shallow lake ceilings, staining the ice with salt. The chaos terrain of Conamara preserves the record of one such episode, frozen in place. The puzzle pieces still identifiable, the matrix between them still reddish-brown with whatever the water carried. The lineae, the long double ridges, trace the paths of tidal stress across the globe, thousands of kilometres of scar tissue. And somewhere in the reconstruction of one unnamed region, 20,000 square kilometres of ice vanished downward, consumed, returned to the interior. Gone, the surface of Europa is the page on which the ocean is writing. Slowly, illegibly, to the untrained eye, but with growing clarity to the instruments that have been pointed at it, and to the scientists who have spent their careers learning to read it. What they have read so far is remarkable. What they expect to read when the next set of instruments arrives, and those instruments are already moving through space as you listen to this, already in transit, already aimed at Jupiter, is likely to be more remarkable still. But before we get to what has just been found and what is being sought, there is one more phenomenon that deserves its moment in this slow narrative. One phenomenon that sits somewhere between the certain and the disputed, that has been glimpsed but not confirmed, that could mean the ocean is not just talking to the surface, but occasionally shouting. The question of whether Europa vents water directly into space, whether the ocean, or something within the ice shell, produces plumes of water vapour that rise hundreds of kilometres above the surface and can be detected from a telescope in orbit around Earth or floating free in the darkness between the planets. Whether Europa breathes. That question has a complicated, unsatisfying, genuinely honest answer. And it is the right place to pause as this part of the story settles into the quiet before the next. There is something to be said for pausing before an answer, for allowing a question to sit in the air the way a single note lingers after a string is plucked. Still present, still resonant, not yet resolved. The plume question is that kind of question. It reaches toward a particular possibility that Europa's ocean is not simply resting beneath its ice in quiet confinement, but occasionally erupting upward through cracks and channels, venting water into space itself, breathing outward into the vacuum the way a whale surfaces to exhale. That question deserves patience. It deserves the honest accounting it will receive. But first there is more surface, more ice, more of the text that 40 million square kilometres of frozen crust has been composing for longer than our species has existed in a script we are only beginning to learn to read. The plumes, if they are real, are one kind of message. The surface markings are another. And the surface markings have the advantage of being there every time we look. So let the mind settle a little lower. Let it drift across the ice at something close to walking pace, at the speed of attention when attention is not in a hurry. And look at what is written there. The lineae. The word comes from the Latin for lines. It is precisely what they appear to be at first glance, long, dark streaks drawn across the face of Europa in every direction, crossing each other at all angles, cutting through the smooth plains and through the churned rubble of the chaos regions alike, extending for hundreds or thousands of kilometres without obvious interruption. From a distance they look like the cracks in an old ceramic glaze, or the surface of dried clay after weeks without rain, or the pattern a hard-boiled egg makes when you roll it across a table and the shell fractures into 1,000 small islands of white, each outlined in a line of slightly crumpled membrane. From above, from far enough away, Europa looks like something that has been cracked and held together. Just barely. But the lineae are not random. That is the thing that becomes clear when you stop looking at the pattern as decoration and start looking at it as data. The lineae are not the random fractures of a frozen surface, cracking wherever it was weakest. They are not chaotic. They are, in many regions, almost disturbingly ordered because they follow the direction of the stress that caused them. And the stress that caused them changes direction as Europa moves along its orbit. The tidal force that Jupiter exerts on Europa is not constant, and it does not always pull from the same direction. Europa's orbit is slightly elliptical, kept that way by the gravitational tug-of-war with Io and Ganymede. So as Europa swings closer to Jupiter and then arcs away, as it moves faster at periapsis and slower at apoapsis, the direction of the maximum tidal stress, the direction along which the moon is most being stretched, rotates slowly. Think of it as a hand wringing a wet cloth, but instead of rotating the cloth in a circle, The hand rotates the direction of the twist, slowly, over the course of a single orbital period. The surface of the Moon, being ice rather than solid rock, responds by cracking along the direction of tension. And then, as the direction of tension changes, it cracks again, slightly offset. And again. Over millions of years, the result is a surface patterned with long, curving fractures. Some of them following graceful arcs across hundreds of kilometers that trace the changing geometry of Jupiter's pull as precisely as a compass needle traces north. Many of Europa's most prominent lineae follow cycloidal paths. Not perfectly straight, not random, but curved in the gentle arcs that tidal stress modeling predicts if you know the orbital parameters and you know how the stress direction rotates. The curves are, in a very real sense, a record of orbital mechanics inscribed in ice. A frozen seismograph that has been running continuously for longer than anything alive on Earth. The match between the observed curves and the predicted stress patterns is close enough to be considered direct physical evidence that tidal flexing is actively shaping the surface in real time, or at least has been doing so continuously up until very recently in geological terms. The lineae are also, in many cases, not single cracks, but double structures. Two parallel ridges with a shallow trough between them, sometimes with the trough showing a slightly different color from the surrounding surface, sometimes nearly indistinguishable except in the highest resolution images. Double ridges. The same feature over and over in different sizes and different locations, as if the Moon has a preferred way of forming them. For a long time the mechanism was debated. The obvious suggestion that tidal stress opens a crack, liquid water wells up partway, and the water refreezes, pushing both edges of the crack upward like two loaves of bread rising on either side of a seam, was plausible, but hard to confirm. You would need to see the same process happening somewhere else, somewhere you could actually visit and test and measure. In 2022, a team led by Riley Kullberg at Stanford found exactly that, a double ridge in the Greenland ice sheet. Not on Europa, on Earth, in a place people have drilled and measured and analyzed with a full range of instruments that simply don't exist yet for a moon 500 million kilometers away. The Greenland structure is smaller and it formed under very different temperature conditions. And it is not the product of tidal flexing. But the geometry is strikingly similar, and the process Kullberg's team identified at the Greenland site was this: liquid water trapped within the ice sheet, a shallow reservoir or sill of meltwater sitting inside the cold ice rather than flowing out, slowly refroze from the outside inward. As cold gradually reclaimed the water that warmth had briefly liberated. As the water froze, it expanded. The expanding ice had nowhere to go except up, and it pushed the surface of the ice sheet up on both sides of the buried reservoir, forming two parallel ridges with a trough between them, following the line of the buried water below. The Kullberg team published their analysis in Nature Communications, and it pointed at Europa with quiet directness. If the same process is operating on Europa, and the geometry of the ridges suggests it might be, then the double ridges are not just scars from tension, they are surface expressions of water moving through the ice shell. Not water deep in the ocean 60 or 80 or 100 kilometers below. Water relatively close. Water that was once liquid, and that was in the process of refreezing when the surface was pushed into the shape we see. The shallow water that Brittany Schmidt's chaos terrain model required is, in this interpretation, not confined to the large collapse regions. It is moving through cracks and pores and passages throughout the ice shell, rising occasionally into thin films and shallow reservoirs, refreezing, expanding, lifting the surface into ridges, and then doing it again elsewhere, somewhere else, sometime later. The ice is not static. It is not a sealed container. It is more like a sponge, a cold, rigid sponge through which small amounts of liquid water occasionally move, leaving traces of their passage in the geometry of the surface they touch. Sit with that for a moment. The largest feature type on Europa, the double ridges, which cover more of the surface than anything else, which cross and crisscross and create the gridded, fractured pattern that gives the moon its distinctive look. May be, each one of them, the mark left behind by a small pulse of water moving upward through the ice. Thousands of them, spanning the entire globe, each one a signature of a process that has been repeating continuously, slowly, for tens of millions of years. That is how much movement there has been. Not dramatic, not sudden, not a single catastrophic event, but persistent, patient. Geological scale motion sustained by the same tidal engine that keeps the deep ocean liquid. And then there is the question of the shell itself. Not what is written on it, but how it moves as a whole. The ice shell of Europa floats. This sounds obvious. Ice is less dense than water, so of course it floats, but the implications are less obvious than they first appear. The shell does not merely sit atop the ocean the way lake ice sits on a still pond. It is decoupled from the rocky body beneath the ocean. The ocean is not a thin layer between rock and ice. It is a substantial buffer, tens of kilometers of liquid saltwater, separating the icy outer shell from the rigid silicate interior below. The shell and the interior are not mechanically attached. The only thing connecting them is gravity, which keeps the shell pulled against the interior, and the slow friction of tidal flexing. But there is nothing to prevent the shell from rotating over long timescales at a slightly different rate than the rocky body it surrounds. The evidence suggests this has happened, or is happening, or has been happening slowly enough that we can see its cumulative signature without being able to watch it in real time. The crack patterns on Europa's surface, the lineae, the ridges, the cycloidal arcs, do not perfectly align with the locations that the current tidal stress field would predict if the shell were perfectly locked to the interior. There are offsets. Small ones, but consistent. Planetary scientists call this non-synchronous rotation, or in some versions of the analysis, true polar wander. The shell has apparently shifted its orientation relative to the deep interior and relative to Jupiter. How much and how fast is uncertain. It may be a fraction of a degree, it may be many degrees over hundreds of millions of years, but the implication is physically clear. The shell is not fixed. It moves. It can move, because there is nothing rigid holding it in place. The ocean between the shell and the core is in effect a lubricating layer, an enormous global bearing on which the outer skin of the moon slowly rotates. Think of it this way. Imagine a hard boiled egg, except the egg has been transformed so that the white has liquefied while the shell remains solid. You hold the shell in your hand. Inside, the yolk, the rocky core, sits in a bath of liquid. If you nudge the shell moves, but the yolk doesn't. Not immediately. The shell can turn slightly relative to the yolk because the liquid between them allows it. Europa is that egg. The shell is the outer ice, kilometers thick, carrying all the chaos terrain and the lineae and the double ridges on its outer surface. The liquid white is the ocean. The yolk is the silicate and iron interior, orbiting Jupiter in perfect synchrony the way a tidally locked moon should. And the shell, slowly, over geological time, has drifted. The crack patterns preserve the memory of where the shell was when those cracks formed. Earlier cracks are offset from later ones in ways that reveal the drift. The surface is not just a record of the ocean's chemistry and the tidal stress field. It is also a record of the shell's own history of motion. A series of overlapping exposures, like a long exposure photograph of a slowly rotating object, each layer of fractures slightly rotated relative to the one beneath. This is Europa not as a static ice world, but as a system in constant, slow negotiation with itself. The ocean below moves in ways we can only infer. The ice above moves in ways we can read, imperfectly, in the distribution of fractures across the globe. And between them, the chemistry of the ocean finds its way upward, carried by water moving through the ice, emerging on the surface in the form of colour. The colours of Europa. Most of the surface is white or pale yellowish white, ice, reflecting sunlight, cold and bright, and featureless from a distance. But the lineae are not white. The chaos terrain is not uniformly white. Running along the ridges and seeping across the disrupted blocks of the chaos regions is colour, a reddish-brown, in many places. That stands out against the background ice, the way rust stands out against galvanized metal, or the way an old stain shows through a white cloth that has been washed many times, but not enough. The colour is not decorative. The colour is chemistry. For decades, the reddish-brown material was assumed to be salts, specifically magnesium sulfate, which sounds technical, but is essentially the mineral we call Epsom salt. The same compound people dissolve in a warm bath. The assumption was that Europa's ocean was a cold, mineral-rich solution dominated by magnesium sulfate, and that the upwelling of this solution into the ice and onto the surface was responsible for the characteristic discoloration. It was a reasonable assumption. Magnesium sulfate is not exotic chemistry. It is common in icy environments. It would be consistent with certain models of how the ocean formed and what it might contain. But in 2019, the assumption was refined in an important direction. A team led by Samantha Trumbo, working with Michael Brown and Kevin Hand, used the Hubble Space Telescope to observe a region on Europa called Terra Regio, one of the most extensively disrupted areas of chaos, terrain on the surface, a place where the original ice crust has been broken down almost completely and replaced with the churned, refrozen rubble of what was once, apparently, an active zone of upwelling. They analysed the colour in Terra Regio carefully, looking at the specific wavelengths of light being reflected and absorbed by the surface material. What they found was not magnesium sulfate, or not primarily. What the spectral signature matched most closely was sodium chloride that had been exposed to intense radiation. Sodium chloride, the molecule we call table salt, the mineral that seasons food, that preserves fish, that concentrates in the evaporation basins of every salt flat on Earth, that fills the oceans of our own world in vast quantities and gives seawater its characteristic taste. Ordinary, familiar, ubiquitous salt. On the surface of Europa. In Terra Regio. The distinction matters more than it might seem. Magnesium sulfate and sodium chloride are both salts in the chemical sense, but they imply different ocean chemistries. An ocean dominated by sodium chloride, common salt, is, in its basic ionic composition, more similar to Earth's oceans than an Epsom salt ocean would be. It suggests a more familiar kind of brine. A brine that interacts with rock and mineral in ways that are, at least by Earth analogy, more hospitable to the kinds of chemistry that life on our world relies on. This does not mean the ocean is Earth-like in temperature, or pressure, or depth, or composition overall. It does not mean the chemistry is identical or even close. But it was a shift in the direction of familiarity rather than away from it, and it was grounded not in a model or a speculation, but in an actual spectral measurement of actual material sitting on the surface of Europa. And the reason the sodium chloride shows up where it does, concentrated in the chaos terrain, in Terra Regio, in the most disrupted parts of the surface, is exactly what the geology predicts. If the chaos terrain is where the ocean talks to the surface, where upwelling brings ocean water into the ice shell and eventually to the exterior, then the chaos terrain is where you would expect to find the salt the ocean left behind as its water refroze. Evaporation and refreezing are different processes, but both concentrate solutes. As ocean water or ocean-saturated brine works its way upward through the ice and eventually reaches the surface or near surface, the water locks back into ice crystals and the dissolved salts are excluded, pushed out of the growing ice lattice, the way a slow freeze gradually pushes the minerals out of a freezing solution, concentrating them into the last liquid to freeze. What remains on the surface is the chemical residue of ocean water, salt. Then Jupiter's radiation does what Jupiter's radiation does. The intense flux of high-energy particles bombarding Europa's surface every second interacts with the sodium chloride and transforms it. The radiation breaks and rearranges the molecular bonds, producing new compounds, some of which absorb particular wavelengths of light in ways that pure sodium chloride does not. The result is the reddish-brown coloration. The color itself is radiation damage. The color is what salt from Europa's ocean looks like after it has been irradiated for long enough by the most powerful magnetic engine in the solar system outside the Sun. Stand back from that image for a moment. The streaks along the lineae, the stains spreading through Terra Regio, the reddish marks across the chaos terrain. These are not random coloring. They are, if the interpretation is correct, the visible signature of ocean water that has travelled upward through tens or hundreds of kilometres of ice, reached a surface it was never meant to reach, and then been chemically transformed by radiation into something that changes the colour of the ice it once saturated. The ocean is marking its own roof from the inside. The stains on Europa's surface may be the only way the ocean can write in a language our instruments can read from orbit around Jupiter or from a telescope floating in space near Earth. And they are more than decorative. They are informative. Because what was true of sodium chloride in Terra Regio, that its presence tells us something about the ocean's ionic composition, is also true of everything else the ocean might carry upward. Every compound, every molecule, every dissolved mineral that makes it from the ocean to the surface is a data point about the ocean's chemistry. And the surface, with all its chaos terrain and lineae and double ridges, is offering those data points continuously, laid out for any instrument sensitive enough to read the specific wavelengths of light they absorb or reflect. This is why the surface matters so much. Scientifically, it is not just the lid on the ocean. It is the ocean's autobiography, written in chemistry, preserved in ice, spread across 40 million square kilometers of moon. The challenge is reading it. And that challenge is complicated by a disagreement that runs through the heart of Europa science like one of the great lineae themselves, dividing the field into two interpretations of the same surface, two visions of what is happening beneath it, and two sets of predictions about what the ocean is actually like. The shell is either thin or thick, and the answer changes almost everything. The question of ice shell thickness has been debated for as long as scientists have been taking Europa's surface seriously, which is to say since the Voyager images arrived in the late 1970s and the Galileo images sharpened the picture in the 1990s and early 2000s. It is not a settled question. It remains genuinely open. And it is not a question with a clear compromise position. It is not the case that everyone agrees the shell is probably somewhere in the middle. The data genuinely support different interpretations, and thoughtful, rigorous scientists have defended positions on both ends of the range. The thin ice hypothesis holds that the ice shell is only a few kilometers thick, perhaps 3 to 10 kilometers in the thinnest regions, with the ocean sitting quite close to the surface. In this picture, the chaos terrain forms easily because only a thin layer of ice separates the ocean from the surface, and the ocean's heat and chemistry can reach upward relatively quickly. Plumes, if they exist, would erupt through this thin shell without great difficulty. Future landers could drill through to the ocean without needing technology far beyond what we currently possess. The surface would be in rapid, active communication with the ocean below. The thick ice hypothesis holds that the shell is 15 to 25 kilometers thick, or possibly even thicker in places, a substantial icy mantle that insulates the ocean from the vacuum above and from the radiation that bombards the surface. In this picture, the chaos terrain still forms, but through convective processes within the thick ice, warm, buoyant ice rising slowly from the bottom of the shell, and cold, dense ice sinking, carrying heat and perhaps chemistry, but not literal ocean water through most of the shell's thickness. The shallow liquid water pockets that Brittany Schmidt proposed, the lakes within the ice, a few kilometers down, would be real in this model, but they would be isolated features fed by ice shell dynamics rather than direct ocean upwelling. Drilling to the ocean from the surface in the thick ice scenario would require burrowing through 20 kilometers of ice before reaching liquid water. That is not a near-term prospect, with any technology being seriously discussed. The honest position is that we do not know which is correct. Both are physically plausible. Both are consistent with the available data at current resolutions. The chaos terrain can be explained by either model. The lineae are consistent with both. The double ridges, following the Kullberg interpretation, suggest liquid water close to the surface, which tilts slightly toward thin ice. But the thickness at which water can still move through the ice in shallow sills is not perfectly constrained. The non-synchronous rotation of the shell tilts slightly toward thin ice as well, because a thinner, less viscous shell would decouple from the interior more readily. But tilts are not proofs. The crater count sets a minimum constraint. The surface age of roughly 40 to 90 million years means the shell is being resurfaced on that timescale, but the mechanism of resurfacing is exactly what the thin versus thick debate is arguing over. Convection within a thick shell can resurface just as surely as direct upwelling from a thin shell. The craters do not discriminate between the two mechanisms. The magnetic induction data from Galileo gave some information about the ocean's depth and salinity, but the resolution of those measurements was not sufficient to constrain the ice shell thickness to better than a broad range. An ocean that begins at 3 kilometers below the surface and one that begins at 25 kilometers below the surface would produce broadly similar magnetic induction signatures given the quality of data Galileo was able to collect during its close flybys. What is needed, and what has not yet been available is ice-penetrating radar. The same technology used to map the ice sheets of Antarctica and Greenland from aircraft, radio waves sent downward through ice at specific frequencies, reflecting off internal layers and off the base of the ice where it meets liquid water below. On Earth, this works beautifully. The radar reflections come back crisp and clear and interpretable. On Europa, the technique faces a complication. Jupiter's radiation environment produces radio emissions across a wide range of frequencies that could drown out the radar return. Designing a radar that can work in that environment requires careful engineering. But it has been done. The instrument exists. It is called REASON, Radar for Europa Assessment and Sounding, Ocean to Near Surface. And it is one of the core science instruments aboard a spacecraft that is right now, as you listen to this, crossing the space between Earth and Jupiter. But that is a few steps ahead of where we are. What matters now in this part of the story is that the thin ice versus thick ice debate is not a peripheral disagreement among specialists. It is central to every practical question about Europa. If the ice is thin, the ocean is accessible. The surface chemistry is in rapid exchange with the ocean below. Plumes are mechanically easier to produce and perhaps more frequent. A future mission could conceivably drill or melt its way through to the ocean in a matter of years. If the ice is thick, the ocean is sealed behind a wall of cold that will require extraordinary effort to breach. And the surface chemistry we observe is at least partly the product of ice shell dynamics rather than direct ocean communication. The outlook for direct sampling of the ocean on any near-term human timescale becomes considerably more challenging. Both possibilities are consistent with a liquid ocean existing. The ocean is not in doubt. The magnetic induction evidence, the tidal heating mechanism, the surface geology, all of these point to a global ocean as the most straightforward explanation for what is observed. But what the ocean is like, how deep it begins, how thick the lid above it, how actively it exchanges material with the surface, these remain genuinely open questions. Questions without clean answers in the current dataset, which is precisely why the questions matter so much. A question without an answer is an invitation to look harder, and the answer, when it comes, will not come from a model or a theory or an extrapolation from a dataset gathered a quarter of a century ago by a spacecraft that was never specifically designed to answer this question in full. It will come from new measurements, new data. A new set of instruments built specifically for this purpose, engineered to operate in the most hostile radiation environment in the solar system outside the Sun itself, placed in the precise trajectory and orbit needed to collect what no previous mission has been able to collect. The surface of Europa has been telling its story for 40 million years in the language of ice mechanics and ocean chemistry and tidal stress. We have learned to read some of it, enough to know that the story is extraordinary, enough to know that the ocean below is real and large and old and restless in ways that should not be possible at this distance from the warmth of the sun. Enough to know that the ice above it is not a static lid, but a dynamic system, cracking, drifting, subducting, admitting water, hosting chaos, carrying salt from the depths to the surface, and bearing the chemical signatures of an ocean we have still never directly touched. And enough to know that there are questions the surface alone cannot answer. Questions that will require looking not just at what the ice does, but at what comes through it, or what rises above it. The thin film of gas that hugs Europa's surface, so tenuous it barely qualifies as an atmosphere, so sparse it would be a near vacuum by any standard we could survive. carries its own kind of information. Information about what is happening where the ice meets the near vacuum of space. Information that has been, at various times and under various observing conditions, surprising. The lineae are the surface's long sentences. The chaos terrain is its punctuation. The salt stains in Terra Regio are its signature. And somewhere, in between all of that, there may be something else. Something more sudden. Something that rises rather than creeping. Something that, if it is real and if we can find it and taste it, would be the closest thing we have ever had to a direct sample of what lies beneath. The question of whether Europa breathes is not yet answered, but the evidence that has been gathered piece by piece, instrument by instrument, over 3 decades of observations from Earth orbit and from the Jupiter system has a shape to it. The shape of something that is real but intermittent, present but unpredictable, detectable on some nights and invisible on others. The shape of something that the next generation of instruments may finally be able to hold still long enough to read with confidence. That evidence begins with a telescope and a set of observations made over 2 years in the first half of the 2010s by a team watching Europa's south pole for signs of water rising against the darkness of space. In December of 2012, a team of astronomers using the Hubble Space Telescope turned their attention to Europa's south pole and found something that did not belong in the data they expected to collect. Lorenz Roth and his colleagues had been watching Europa transit the face of Jupiter, passing across the disk of the planet so that any material venting from the moon's surface would be silhouetted against the bright background, and in those silhouettes, faint and contested but unmistakably present in at least some of the observations, there was absorption consistent with water vapor. A plume rising roughly 200 kilometers above the southern pole, higher than most of the clouds in Earth's atmosphere, stacked many times over. A column of water rising from a body whose surface temperature sits near -160 degrees Celsius, in a region where nothing should be rising, erupting, or venting into the vacuum of space. The problem was that it was not always there. This is the thing about Europa that makes it so difficult to speak about with confidence. When you look for the same thing twice, you do not always find it. The plume, if it was a plume, and the team was careful to say if, appeared in some of Hubble's observing windows and was absent from others. The signal rose above noise on certain nights and vanished against the background on nights that followed. That intermittency is not itself evidence against the plumes being real. Geysers on Earth are intermittent. Old Faithful is predictable only because it has been watched long enough and in enough detail to map its cycle. If Europa has something like geysers, they may well operate on timescales we haven't yet characterized, triggered by tidal stresses that wax and wane over the course of each orbit. Venting when the ice is pulled apart and quieting when the compression returns. But the scientific standard for a detection is that the detection can be reproduced. And for the Europa plumes, that standard has not yet been cleanly met. The Hubble observations of 2012 and then through 2014 represent the first serious evidence that something is being expelled from Europa's interior and reaching space. They are not the last evidence. But they are also not confirmation in the way that a repeated, corroborated measurement from multiple independent instruments would be. So they sit in the dossier of things that are probably real, possibly real, maybe real. The kind of result that keeps a scientific community awake and scanning their data, looking for the same shape of signal in other places. And one team did find it, in a place they had not thought to look. In 2018, a group led by Xianzhi Jia published a paper in Nature Astronomy describing a reanalysis of data collected 21 years earlier in 1997 when the Galileo spacecraft made a close pass over Europa. The flyby was called E12. Galileo came within roughly 200 kilometers of the surface at closest approach, close enough that if there was a plume erupting in its path, the spacecraft would have passed directly through it. At the time, the flyby was considered routine. The magnetic field data and the plasma wave readings were collected and archived. The mission moved on to its next target, its next orbit around Jupiter, its next set of encounters with the moons. Nobody had been looking for plumes in that data because nobody had strong reason to expect them yet. The Hubble result came 15 years later. When Jia's team went back to the archived magnetometer and plasma wave instrument records from E12 and searched specifically for the kind of disturbance that a dense column of ionized water vapor would create as a spacecraft flew through it, they found a signature, a sharp localized change in the magnetic field. An anomaly in the plasma data, both consistent in shape and magnitude, with Galileo having flown through a plume of material rising from Europa's interior and reaching the altitude of the spacecraft's trajectory. Galileo may have sampled the ocean in 1997, and no one realized it until 2018. There is something that stops you when you sit with that for a moment. A spacecraft built by human hands, launched in 1989, travelling hundreds of millions of kilometres, making a pass close enough to a moon to briefly feel the electrical and chemical signature of water erupting from beneath kilometres of ice, and the data was there in the archive the whole time, patient, unread for that particular purpose, waiting for someone to ask the right question of it. The ocean reached up and touched our spacecraft. We just did not know it yet. The Keck result, published the following year in 2019, added another data point that exists at the edge of confidence rather than firmly inside it. Lucas Paganini and colleagues, using the Keck Observatory in Hawaii, reported a direct spectroscopic detection of water vapor above Europa's surface. They observed Europa across many separate nights. On one of those nights, there it was, water, on all the others, nothing, one detection across an extensive campaign of looking. One is not zero. But one is also not a pattern. It is a data point with enormous implications if it holds up, and an intriguing anomaly if it turns out to be noise. Paganini's team was honest about this. The water vapor, if real, was being produced at a rate equivalent to the minimum detectable threshold of the instrument. It sits at the frontier of what can be resolved from ground-based telescopes across the distance between Earth and Jupiter. And then there is what JOEST did not see. When the James Webb Space Telescope turned its near-infrared detectors toward Europa in 2022 and 2023. It was performing observations that the science community had long anticipated. Webb is the most sensitive space telescope ever deployed. Its ability to detect trace amounts of gas and chemical signatures over vast distances exceeds anything Hubble or Keck can achieve by significant margins. If Europa's plumes were ongoing and vigorous, Webb would find them. Webb looked. Webb did not find active venting during its observation window. This is an honest negative result, and it matters. It does not erase the Hubble detections or the Galileo retroactive evidence or the single Keck night of water vapor. What it does is constrain the picture. If plumes exist, they are not constant. They are not the kind of sustained. continuous eruption that would register on any instrument pointed at Europa on any given night. They are rare, intermittent, possibly tied to specific stress patterns in the ice, possibly connected to particular regions of the surface where the shell is thin or where a shallow subsurface lake is pressing upward against its ceiling. So the honest summary of where the science stands on Europa's plumes is this. There is evidence from multiple independent instruments and one retroactive archival find that something consistent with water vapour has been detected erupting from Europa's surface on at least a few separate occasions over 3 decades of observation. That evidence is real and taken seriously by the planetary science community. It has not been confirmed as a stable, repeatable phenomenon that can be counted on to appear whenever you look. The plumes, if they are plumes, are Europa being occasional about the secret it is carrying. And the next set of instruments in line to resolve that question are already in flight. But before arriving at what is in flight and what it will attempt to answer, there are 2 results from 2023 and 2024 that arrived while the spacecraft was still being built and tested and then launched. And those 2 results changed the framing of what the mission is actually flying toward. One of them made the case for life more interesting than it had been before. The other made the case harder. And they arrived within roughly 6 months of each other, which is the kind of thing that happens in science when instruments finally become sensitive enough to see what was always there. The first result came from Webb in September of 2023. 2 papers, published simultaneously in the journal Science, one led by Samantha Trumbo and Mike Brown. The other by Geronimo Villanueva and colleagues described what Webb found when it examined Europa's surface chemistry in near-infrared light. Not plumes, but something in some ways more significant, carbon dioxide. Concentrated, measurable, localized carbon dioxide sitting on the surface of Europa's ice, found in greatest abundance in a region of chaos terrain called Terra Regio. Carbon dioxide is not unusual in the outer solar system. It can be delivered by meteorites, comets, interplanetary dust. It can be produced by radiation chemistry when carbon-bearing compounds sitting on an icy surface are bombarded by energetic particles. So the detection alone does not close the case. What Trumbo, Brown, Villanueva, and their respective teams did was look carefully at where the carbon dioxide was concentrated, how it was distributed, and what that distribution implied about its origin. It was in Terra Regio, the chaos terrain, the same churned, shattered, refrozen region where the surface has clearly been disrupted by something rising from below, where ice rafts have been broken and shuffled and reset into their frozen jigsaw, where the surface is geologically young, even by Europa's already young standards. The carbon was not uniformly spread across the ice. It was concentrated precisely where the ice is most actively interacting with what lies beneath it. And its abundance and distribution were most consistent in the team's analysis, not with external delivery and not with surface radiation chemistry, but with the carbon having come from the internal ocean and been carried to the surface through the same processes of upwelling and disruption that created the chaos terrain itself. The ocean has carbon in it. That sentence carries more weight than it might initially seem. Carbon is one of the foundational ingredients of life as we have ever encountered it. Every living thing on Earth is carbon-based. The organic molecules that are the building blocks of biology, amino acids, nucleotides, the long chains of carbon atoms that carry energy and information, are made of carbon combined with hydrogen and oxygen and nitrogen and other elements. The presence of carbon in Europa's ocean does not mean life is there, but its absence would have been a significant mark against the possibility. And now the absence has been ruled out. The ocean carries carbon, and that carbon is reaching the surface in the places where the ice is most restless. The Webb papers noted another thing. In the same observations that detected the carbon dioxide, there was no active plume. The carbon is not rising in a dramatic eruption. It is being carried upward more slowly through the same geological processes that churn the chaos terrain over millions of years, through the same mechanism by which the ice rafts float and rotate and refreeze, pulling material from below into the surface. This connects the chemistry of part 2 of this story directly to the geology of part 3. The restless ice and the carbon signal are the same process, seen at different scales. So in September of 2023, the community received confirmation, the strongest chemical evidence yet, that Europa's ocean contains at least one critical ingredient for life, and that the ocean is actively communicating with the surface we can observe. The mood in the field tilted cautiously upward. The picture was becoming richer. Then came March of 2024. A paper by Jamie Saleh and colleagues published in Nature Astronomy reported results from NASA's Juno spacecraft. Juno is primarily a Jupiter mission. It has been orbiting the gas giant since 2016, studying its atmosphere, magnetic field, and interior. But its mission has been extended and its orbit adjusted to allow close flybys of several of Jupiter's moons, and on September 29, 2022, Juno made a close approach to Europa. Closest approach was roughly 354 kilometers above the surface, close enough for the spacecraft's instruments to meaningfully sample the environment immediately surrounding the Moon. One of Juno's instruments is called JADE, Jovian Auroral Distributions Experiment. It was designed to measure energetic particles in Jupiter's magnetosphere. But during the Europa flyby, it was positioned to detect the energetic oxygen ions being produced at Europa's surface. The mechanism is this: Jupiter's radiation belts, among the most intense in the solar system, constantly bombard Europa's ice with high-energy electrons and ions. When those particles slam into water ice, they split the water molecules apart, releasing hydrogen and oxygen. The hydrogen, being very light, tends to escape into space. The oxygen and hydrogen peroxide tend to stay, accumulating on the surface or becoming part of the thin exosphere. This is the process that gives Europa its trace oxygen atmosphere, which is not an atmosphere in any sense that would help a living thing breathe. It is a near-vacuum exosphere, a thin, barely there envelope of molecules that would be millions of times less dense than the air at the top of Earth's highest mountains. But the oxygen it produces matters for a different reason. If cracks in the ice, if chaos terrain upwelling, if any of the geological processes we have been tracing through this story can carry that surface oxygen down into the ocean below, then the ocean has a supply of oxidants, molecules that can give up their oxygen to power chemical reactions, the same way that the oxygen we breathe is used by our cells to release energy from food. On Earth, the oxygen in the atmosphere is what makes complex animal metabolism possible. For Europa's ocean, surface-produced oxygen dropped into the deep water through ice recycling could play an analogous role. Before the Juno flyby result, the estimates for how much oxygen Europa's surface was producing ranged widely. The upper end of some models put the production rate at close to 1,000 kilograms per second, a substantial supply. Other models were lower, but the community had generally not dwelled too long on the pessimistic end of the range, because the middle estimates seemed large enough to make the energy budget question at least plausible. Juno's JADE instrument, measuring the actual oxygen ions being shed from Europa's surface during the September 2022 flyby, returned a number toward the bottom of the range the field had considered, roughly 12 kilograms per second. With uncertainty that spans roughly 6 to 18 kilograms per second, depending on the assumptions built into the analysis, the midpoint of that range is more than an order of magnitude smaller than the upper estimates that had colored the community's optimism. Not zero oxygen, but far less than the most generous models had suggested. 12 kilograms per second sounds like a lot when you say it plainly, but measured against the scale of an ocean that may be 60 to 150 kilometers deep and completely global, measured against the energy needs of any ecosystem that might inhabit that ocean, the number is considerably more modest than hoped. The habitability budget, as the field sometimes calls it, just got smaller. And this is where the story lands a kind of paradox that is genuinely rare in planetary science, because the two results arrived essentially together. Within roughly 6 months of each other, the community learned that Europa's ocean very likely contains carbon, a required ingredient for life as we know it, and that Europa's surface is producing far less oxygen than previous models had assumed, which shrinks the available energy supply for life as we know it. Better evidence for the ocean's chemistry, landing at the same moment that the oxygen budget was trimmed. The picture has not collapsed. Saleh and colleagues were careful to note that their flyby sampled Europa at one location, at one time, under one set of conditions, and that the actual global average production rate could be somewhat different. The Juno result is the most direct measurement of oxygen production we have, and it is enormously valuable, but it is a single point in a system that varies with tidal stresses, radiation flux, surface composition, and the geometry of any given region. Some models also point out that even a limited surface oxygen supply might be enough if the ocean's chemistry is right, if the water contains other oxidants, if the seafloor hosts hydrothermal activity that provides chemical energy from a different source entirely, one that does not depend on radiation from above. That last possibility, the hydrothermal option, is worth pausing on, because it is the ground beneath the feet of everything that has been said about habitability so far. At the base of Europa's ocean, where the water meets the rocky seafloor, the heat driving the whole system comes from tidal flexing of the rock. Where hot rock meets liquid water, chemistry happens. On Earth, the mid-ocean ridges and deep-sea vents, where this process operates, host entire ecosystems. Tubeworms and shrimp and chemosynthetic bacteria that derive their energy not from sunlight but from the chemical reactions at the rock-water interface. These ecosystems exist in complete darkness, under crushing pressure, in water that would boil at surface conditions. They need no sun. They need no ozone layer. They need only the heat and chemistry of the vent. Europa's ocean floor may well have hydrothermal vents. The tidal heating that keeps the ocean liquid has to be depositing that energy somewhere, and the most natural place is the seafloor, where the rocky mantle flexes and warms the water above it. If such vents exist on Europa, then the oxygen budget from the surface matters less, because the vents provide their own chemical energy entirely independent of what the radiation belts are producing in the ice, 2 kilometers or 60 kilometers or 100 kilometers overhead. The Juno result shrinks the habitability window from one direction. The hydrothermal possibility keeps it open from another. And the Webb carbon result sits at the center, telling us the ocean is not chemically inert, not a dead, sterile sea, but a body of water that contains at least one of the molecules life builds itself from. The honest answer to the question of whether Europa could support life is, we still do not know. And the question is now more detailed and specific and interesting than it was before these two results arrived. That is science working correctly. The picture is not simpler, it is sharper. What settles it is not more arguments. What settles it is a spacecraft close enough to read the answer directly. NASA's Europa Clipper launched on October 14, 2024. Riding a SpaceX Falcon Heavy rocket from Kennedy Space Center, it is the largest planetary science spacecraft NASA has ever built to survive one of the most hostile radiation environments in the solar system. Built to taste the chemistry rising from a moon whose surface we can observe and whose interior we can only infer. Built to answer the specific questions that the past 3 decades of observation and the past few years of tightening results have made most urgent. It is already in flight, right now, moving through the solar system on a trajectory that will carry it past Mars in the spring of 2025 and back past Earth in late 2026. Borrowing momentum from each planet's gravity to redirect and accelerate toward the Jupiter system. Gravity assist is the technique of threading a spacecraft through a planet's gravitational field at precisely the right angle so that the planet's orbital motion imparts speed to the spacecraft without any fuel being burned, like a slingshot whose arm is a whole planet. Without these assists, the launch vehicle would not have enough energy to carry Clipper to Jupiter in any reasonable time. With them, the spacecraft arrives at Jupiter in April of 2030, and the first Europa flyby follows not long after. April 2030. That is the answer to the question of when we find out. Not years in the past, not in some vague future, but a specific month, 4 years from now, when a spacecraft that is already crossing the inner solar system at this moment will arrive at the largest planet in our system and begin a campaign of flybys unlike anything ever attempted at Europa. Clipper will not orbit Europa. This is the constraint that surprises many people when they first encounter it, and it is worth understanding clearly. Jupiter's radiation belts do not stop at the edge of Jupiter. They extend out through the Jovian system, and they are especially intense in the region around Europa's orbit. A spacecraft orbiting Europa would be continuously immersed in that radiation. High-energy electrons and ions slamming into its electronics around the clock, degrading its circuits, corrupting its memory, shortening its operational life from years to weeks or months. Clipper's electronics cannot withstand continuous exposure to the radiation environment at Europa's distance. So instead, Clipper orbits Jupiter. Its orbit is designed so that each loop around the giant planet brings it close to Europa for a relatively brief flyby, a few hours of close approach, and then carries it back out of the intense radiation zone, giving its systems time to operate and its instruments time to process and transmit their data. Across the full mission, Clipper will make approximately 49 of these flybys, with closest approaches varying from dozens of kilometers to a few thousand, designed to build up a global picture of Europa from many different angles and distances and orbital geometries. 49 chances to read the moon. The instrument suite aboard Clipper has been designed around the specific questions this mission needs to answer. The ice-penetrating radar, called reason, will send radio pulses through the ice shell and listen for echoes bouncing back from layered interfaces within it, from the underside of the shell, from water pockets within the ice, from the boundary between the ice and the ocean below. This is how Clipper will measure the thickness of the ice shell, resolve the thin ice versus thick ice debate, and hunt for the kind of shallow liquid water bodies that the Schmidt et al. Chaos terrain work suggested might exist only a few kilometers down. The magnetometer, called ECM, will make precise measurements of Europa's induced magnetic field during each flyby, building on what the Galileo mission detected 25 years earlier, but with far greater sensitivity and spatial resolution, capable of mapping how the ocean's electrical properties vary across the globe, which tells scientists about the ocean's salinity, depth, and how those properties change from place to place. The spectrometers, MISE, the mapping imaging spectrometer for Europa, and Europa UVS, the ultraviolet spectrograph, will map the surface chemistry in detail, extending the Webb team's carbon dioxide detection from a single observation into a global compositional portrait. Where is the carbon concentrated? What other organic compounds are present? What does the distribution of salts tell us about the ocean's chemistry? And perhaps the most direct instruments of all are SUDA and MASSPEX, the surface dust mass analyzer, and the EMAS spectrometer for planetary exploration. These instruments are designed to catch and chemically analyze particles, dust and gas ejected from Europa's surface, whether by normal sputtering from radiation bombardment or by active plume activity. If a plume is erupting during a Clipper flyby, SUDA and MASSPEX can taste it. They can tell us what molecules it contains, what salts and organics and gases have been carried up from below. If the Galileo E12 flyby really did pass through a plume in 1997, then Clipper's instruments, orders of magnitude more sensitive and purpose-built for exactly this kind of sampling, will catch what Galileo could only hint at. There is a phrase that gets used in the Clipper mission documentation, and it is worth holding clearly in mind as the spacecraft crosses the solar system on its way to answer the questions laid out across this entire story. The mission's stated objective is to assess Europa's habitability, not to detect life. Habitability, the three conditions that need to be present together for life as we know it to be possible: liquid water, the right chemistry, and a source of energy. Liquid water is already the most probable of the three, established by magnetic induction evidence that goes back to Galileo's flybys in the 1990s. The chemistry column is filling in carbon from below. Salts that look like sodium chloride from Earth, like oceans, the organic complexity the Webb results opened a door toward. The energy column is the one that the Juno oxygen measurement just made more complicated, and the one that the hydrothermal vent possibility keeps in play. Clipper will not tell us whether anything lives in Europa's ocean. Its instruments are not designed to detect a microorganism. What it will tell us is whether the three conditions are sufficiently met that the next mission, a much harder, much more expensive, much more technically demanding mission involving a lander and a drill and instruments designed for biological detection, would be justified in trying. Clipper is the reconnaissance. The landing, if it happens, is what comes after. And that after is decades away at least, pending what Clipper finds. ESA's JUICE mission, the Jupiter Icy Moons Explorer, launched in April of 2023, will arrive in the Jupiter system in 2031, 1 year after Clipper, following its own gravity assist route through the inner solar system. JUICE's primary target is Ganymede, the largest moon in the solar system and the only moon known to generate its own magnetic field. But JUICE will also make a couple of Europa flybys during its approach and initial time in the Jupiter system. A second set of instruments, a second set of perspectives on the same moon. The decade of the 2030s is the decade when Europa gets the closest scientific scrutiny it has ever received from multiple spacecraft, with instruments built on everything the past 30 years of observation have taught us to look for. In the meantime, the question sits exactly where it has always sat, just a little more precisely outlined than before, beneath somewhere between 60 and 150 kilometers of water, under a moving, cracking, salted, carbon-stained ice shell that is younger than the last dinosaurs and older than any geological surface we expected to find so active this far from the Sun. In a darkness unbroken by any photon from a star, possibly warmed by vents at the rocky floor, where the tidal flexing of a small moon orbiting a giant planet generates enough heat to keep water liquid at the edge of the solar system. Somewhere in all of that, the question of whether we are alone in this solar system might have an answer. We found the carbon there. We measured the oxygen being made at the surface and found less than we hoped. We found salts that look like ordinary sea salt from oceans we know. We found what may have been a plume sampled by a spacecraft we sent in a different decade for different reasons, recognized only when the right question was finally asked of data that had been sitting patiently in an archive for 21 years. Every piece of evidence gathered has required us to work for it, to re-examine old data with new eyes, to send instruments across hundreds of millions of kilometers and wait years for the light-speed delay of the returned signal. There is no shortcut, and there is no satellite uplink from beneath Europa's ice that will tell us what we want to know before the spacecraft we sent arrives to ask in person. Europa Clipper carries, on a metal plate affixed to the spacecraft, a poem by the United States poet laureate Ada Lim called In Praise of Mystery. It also carries a silicon chip bearing roughly 2.6 million names submitted by members of the public, now crossing the solar system toward a moon whose ocean we have never touched and whose floor we have never mapped. That plate and that chip will arrive at Europa in 2030. They will make approximately 49 close passes over the chaos terrain and the lineae and the salt stains and the places where plumes may or may not be venting into the dark. The spacecraft will not land. It cannot land. The radiation would kill it. But it will read the moon as carefully as anything we have ever sent anywhere has ever read anything. And whatever it learns, whether the ice is thin or thick, whether the plumes are real and chemical and filled with ocean water, whether the oxygen supply is as constrained as the Juno measurement suggests, or whether the hydrothermal floor compensates for what the surface cannot deliver, those answers will come back across the distance, travel at the speed of light, and arrive at antenna dishes on Earth, like the ones we have always used to listen to what our spacecraft find, and the people who built those instruments and waited through the years of cruise and the years of flybys will read them, and the picture will sharpen in a way it has never sharpened before. 4 years from now, roughly, give or take the schedule that all spacecraft carry with them like a held breath. So tonight, this is what we know. A moon smaller than Earth's moon holds more than twice the water of every ocean on Earth combined, because the water is not a thin coat on a rocky sphere, but a global shell roughly 100 kilometers thick, most of it liquid. kept from freezing by the same tidal forces that cause Europa's ice to crack and shift and subduct and refreeze in the slow, grinding motion of a world that cannot hold still. That ocean has been inferred from a magnetic wobble we detected with a spacecraft that also, it turns out, may have flown through an eruption of that ocean's water and not known it for 21 years. The surface above it is stained with salt that looks like the salt in our own seas. It carries carbon dioxide, concentrated exactly where the ice has been most disrupted by what lies beneath. It makes oxygen from the radiation that bombards it, but far less of that oxygen than the most optimistic models wanted. And somewhere at the bottom of that ocean, where the tidal heating has to go somewhere, there may be vents in the rock producing chemistry that has nothing to do with any of the oxygen or sunlight or surface processes we have spent so much time tracing. We do not know if anything lives there. The science does not allow us to say it does. But the science no longer allows us to dismiss it easily, either. The questions have gotten harder and more specific and more interesting, which is what real knowledge looks like when it is accumulating, not a smooth march toward yes or no, but a tightening, a sharpening, a slow convergence on what the answer might actually be rather than what we hoped it would be. The ice above that ocean will not sit still. The carbon from below is already on the surface, already being read by our telescopes. A spacecraft we built is already on its way. What you have been listening to tonight is not a story with a clean ending. It is a story paused mid-sentence, with the next line being written by instruments crossing the inner solar system at this moment, destined for a moon they will not reach for 4 more years. The end of this particular chapter lands in 2030 or sometime after, when the data comes in and the scientists read it and the picture either opens toward life or closes toward a beautifully complex but lifeless sea. Both of those outcomes would be extraordinary. A lifeless Europa, with its tidal engine and its global water and its carbon chemistry and its restless ice, would still be one of the most remarkable objects our solar system contains. A lesson in how much complexity and motion and geological richness can exist in a place we assumed was simply cold and still and dead. And a Europa with life, even microbial life, even the simplest chemosynthetic organisms huddled around a hydrothermal vent in the absolute dark, would change the meaning of everything else we think we know about where life can begin and how rarely or how readily it does. If you had to bet, and the scientists working on this question spend their careers not betting, holding the uncertainty with respect, the honest answer is that we genuinely do not know which way it goes. The carbon is there, the oxygen is scarcer than we hoped, the water is vast, and the tidal heating is real, and the hydrothermal possibility remains unruled out. That is a live scientific question. It deserves the spacecraft we sent, and it will deserve the patience we have to carry through the years until the answer comes back. For now, though, pull that closer around you. Let the distance settle. Think about the fact that somewhere out there, past Mars and past the asteroid belt and approaching the immense gravitational cathedral of Jupiter, there is a spacecraft carrying 2.6 million names and a poem about mystery, on its way to a moon whose surface is younger than the creatures that used to walk this earth, whose ocean was inferred from a magnetic ghost, whose ice carries the chemical signature of a sea we have never touched and may never touch in our lifetimes. That is where we are. Not at the end of a mystery, but deep inside it, with better instruments than we have ever had, and more honest uncertainty than the simple story ever offered. The question of whether Europa's ocean holds something alive is, Right now, the most consequential, unanswered question in planetary science, and the machine that may begin to answer it is already flying. Think about what you'd feel if the answer came back yes. Or think about what the scientists who built those instruments feel, knowing they might be the ones who read it first. Good night from up here in orbit. I'll keep watch while you drift.